Okay, null model. Already talked about that. We don't need to go into more detail. Elastic models. Already talked about that. We don't need to go into more detail. Even though on the surface, the thought of these transversely isotropic elastic models is kind of cool, because you could have some sort of bedded material. In reality, people don't use them that often because they don't fail. They're elastic. In reality, if you've got a bedded clay or something like that, it's probably failing. So it's cool on the surface, but it's probably not that useful in practice. But for the elastic models, for a lot of the models, for elastic models, you only need two parameters, two stiffness parameters, right? If it was one-dimensional, it would just be a spring. You just need one stiffness, right? F equals kx. 2D, you need two parameters. Most of the time in the real world, you have Young's modulus, Poisson's ratio. You'll see a lot of the examples in the manual use bulk modulus and shear modulus. And this is for weird mathematical historical reasons that I want to get into. It's certainly possible to convert between them, so I just threw the equations up here on the side. Anyway, you just need two parameters. The more Coulomb model. So the elastic model is useful for testing. It's often useful to set things to be elastic if they're far away from the region of interest. You know that they're never going to fail, because the models actually run faster, because it's not checking every step to see if it's failed, right? So there's actually less calculation going on with these elastic models. So if you have 100,000 zones outside of the region of interest, you know they're never going to fail. You can set them to be elastic, and things will run fast. More Coulomb model, again, is the workhorse of constitutive models, and most people are familiar with this. Just to throw up the reminder plot here, most of the time people are plotting, when they're talking about more Coulomb, they're plotting shear stress versus normal stress. That's some sort of failure envelope. So you can imagine if you have high normal stress and a low shear stress, you're safe. You have a high shear stress and a low normal stress, you're in the failure zone. You never actually get to this zone, right? What happens is your stress increases, you hit this envelope, and you move it along the envelope. This is a non-admissible state up here above the line, right? So probably you have an intuitive feel for cohesion and friction of materials. I'm guessing I don't need to go into a lot of detail here. There are other, so at a minimum, really, you need the cohesion and the friction, and the Young's modulus and the Poisson's ratio. So use more Coulomb, you really need 4 parameters. Most of the time, you probably want to specify a tension as well, tension cutoff. By default, it assumes that the tension cutoff is 0, which means that it's assuming that you're using a soil and it can't withstand any tension. So if you try to pull this apart at this part, right? Certainly, if you're using a rock or maybe some kind of sticky clay, you might have the ability to support tension, and you can give a tension cutoff that's not 0. If you give a humongous value of tension, you say, oh, I never want this to fail in tension for whatever reason. I don't care about the tension part of it. I'm just going to set it to be like 1E20. It doesn't actually set a tension value of 1E20. It sets this value here, which is the intersection of this line with this line. So there is a minimum, no matter how big you set the tension to be, there's a minimum, which is this point right here. I think I have that on a future slide. So cohesion, friction, tension, and optionally dilation. I'll talk a little bit more about dilation. And that also defaults to 0, which is okay a lot of the time. In my world, which is the rock world, we often like to plot things as sigma 1 versus sigma 3 instead of whatever this is, shear stress versus normal stress. You still get a straight line if you're doing more Coulomb, but the intercept is different. So the intercept is the unconfined compressive stress, which turns out to be this. and the slope of the line is some other function of friction. It's like sines and cosines in it. I talked about that. So this, yeah, so if you plot it as sigma 1 versus, this is shear stress versus normal stress, but here's the equations. In sigma 1, sigma 3 world, again, the intercept is, whatever I said before, is think this is the slope of the line if you plot sigma 1 versus sigma 3, but I'd have to go on with that. Okay, and then just, I certainly don't want to go into the math. This is not my area of expertise, but just so that you're aware, I've been showing all these one-dimensional plots of shear stress versus normal stress or whatever. In reality, of course, we have 3D model, and the Moore Coulomb failure criterion is not 3D. It's not a straight line. It's a six-sided shape, right? So again, you can be inside of this thing. You can't be outside of this thing. Imagine taking a slice on sigma 1, sigma 3 space. You know, you get that sort of straight line that we already talked about, but in 3D it's something different. You may or may not have heard this term tresca before, which is just the Moore Coulomb with no friction. If it's a Moore Coulomb with no friction, the slope of the line is 0. It's just got cohesion. And in 3D space, it's just a tube like this rather than an expanding thing, because this thing expands outward because you have friction, right? It gets stronger as you increase the confinement. This is the tension that I already talked about. Yeah. Yeah, if you guys have used Rock Science or Flaxus or Midas or whatever, most of them do implicit solution. And what happens with these programs is they take a big step and they go past the line here, and they have to do a correction and come back down to the line. So they do this sort of iteration. We don't really do that because we're in the explicit world. We get here and we might go like a tiny bit over, but it doesn't really matter. You know, the next step is along the line and along the line and along. So we don't have to do necessarily these corrections in the same way that they do in the implicit world. It just progresses and just follows the line. And for Moore Coulomb, no big deal. But you can imagine these more complicated ones where they have strain softening or some other wacky behavior. Following along that line explicitly is actually pretty efficient, whereas trying to figure out how to do these corrections and come back to some wacky line is much more challenging. So this is kind of the reason that, 25 years ago, they decided to go for the explicit approach, because they assumed that we would be doing complicated nonlinear things. And it's easier to follow those paths with the explicit approach. And implicitly, it's more challenging. I mean, it's certainly possible because these other programs have these models in them, but it certainly becomes more difficult. The fact that we're doing explicit also makes it relatively easy to write your own constitutive models, like I was saying. Because again, you don't need to work out all these return paths and crazy stuff that they have to do. You just put in the stress strain relationship and it just follows it along, right? This makes it a lot easier to do these. Okay, here's more weird math that I'm not going to get into, but again, just so you're aware of the terminology, there's this concept of non-associated versus associated. So, all right, so the way that the soil behaves after it fails depends on the dilation angle, right? So you can imagine intuitively, if something starts shearing, it could potentially open up, right? It's easier to think about it as an actual joint. If it was an actual joint and it was bumpy, it started shearing in such a way that the cohesion was overcome and it really started to slide. You can imagine that might open up, right? And the amount that opens is related to the dilation angle. Same thing could happen in a soil that is not got a joint in it, right? You're sort of forming this failure band or something like that. So essentially this thing is shearing and it could potentially start to dilate, right? That's a relatively well-known phenomenon, especially in like something like a sand where you might have some dilation. So the way that the soil behaves after it reaches the peak strength depends on its dilation. Most of the time, the dilation angle is not equal to the friction angle. So you might have a friction angle of, say, 30 degrees. This thing is not going to dilate at 30 degrees, meaning, for every 1 meter of horizontal movement, you're getting half a meter of vertical movement. That's not realistic, right? So normally the dilation angle is something like 5, maybe 0. So most of the time we're in this, what they call non-associated regime, where the dilation is not equal to the friction. The only reason I'm bringing this up is that there are some analytical solutions for some problems where they assume that the dilation angle is equal to the friction angle, makes the math easier. So these guys can work out the answer to these problems by hand using math and not using models, if they assume that the dilation angle equals the friction angle. We're actually going to do that example a little bit later. In reality, nobody ever does that because that's stupid. The only reason I'm bringing it up is because we're going to show an example later where they have an exact solution that somebody worked out with math. Anyway, there you go. When we do the 3D class, there's a little exercise where we run a bunch of triaxial compression tests and then work out the cohesion and the friction based on those compression tests. We're not going to have time to do that, but if you're like super interested in that, we can. So yeah, obtaining these parameters. I mean, presumably you do these tests in the lab. For soils, that works reasonably well, I guess. You can get a representative sample and do some sort of test and figure out cohesion and friction. For rock, that's actually less useful because you get a little small piece of rock, when in reality, the rock is full of a whole bunch of fractures. So that's not necessarily representative. So certainly in the rock world, you're often kind of guessing at what these properties are. I can talk a little bit more about it when we get to Hook Brown, but even in soils, if you don't have any lab data for whatever reason, you can just go to these kind of tables and have a good guess at what you're doing, and put in realistic numbers and move on with life. And again, certainly if it's like a feasibility study or something and you don't really have any data, you can sort of take a guess at what these properties are and see what you get. So people do that all the time. Then again, here's just some values for dilation angle. Maybe I was a bit wrong. 15 degrees dense sand, less than 10 degrees loose sand. Yeah, 0 for clay. Okay, you know what? We can actually just run this one because I'm probably getting bored of listening to me talk right now. So if you want to start up FLAC2D. If you downloaded everything from ShareFile, we can open this project. If not, either walk around with a key or not worry about it. So if you go to where you put the stuff that you downloaded, day 1, basic material models, examples, Kendall's wedge. There's a project there. This is an example straight out of the manual, but I'm just going to use it to show a couple of interesting things. So this is just making the picture. This is making this model. So it's just a simple chunk of soil with a load on top. Just keep pushing on this load until you get this sort of circular failure. There isn't a sort of analytical solution for this. The amount of load that it can take, this dotted line. So we can measure the load as we load this thing up, see what happens. Eventually, it's going to go essentially more Coulomb material, so it's just going to go plastic. Again, this is a sort of simplified thing because there's actually zero friction. Because to make the math easy, you can work it out what the solution is if you have zero friction. So you could easily draw this thing in Sketch. In this particular case, they did it with commands. And then here's the part, you gotta make this font bigger. So here's the stuff that you need to know. You assign a more Coulomb model, you assign some properties, bulk modulus, shear modulus, cohesion. Another line, they said friction is 0, dilation is 0, tension is some huge number. You don't actually need to put this in here. If you don't specify a property, it goes to 0 by default. So if you're lazy and don't want to type that in, you just don't type it in and it just goes to 0. And then again, you could assign these face groups using the Sketch or the model pane, by clicking on things and giving group names, but here they're just doing commands. Then they're applying a velocity to some grid points on the top. So you're basically just squashing this thing down, right? At constant velocity. A little bit of fish here that's used to calculate the load. So I know you haven't talked about fish yet, but what it's essentially doing is just looking at the reaction forces on those grid points that you're pushing on, working up the forces that are pushing back up, dividing by the area or dividing by the area of that thing. So force over area is stress. Actually, maybe it just adds up the load. It's not even stress. It's just that's basically it. And then you can just run this thing. So you should be able to just click in here, press the green button, and run it, and watch it go here. Click on one of these plots, say velocity. Yeah, man, we didn't type anything here, so as long as you probably don't even. Oh, this one we'll never solve. This is pushing at a constant velocity, and this thing is failing. So it will never solve. If you say solve, it's just going to keep on going forever. It's going to be a disaster. So. Okay, either way, 13,000 steps or 25,000 steps, whichever. Right. Right. I guess if you specify a ratio that's smaller, it'll probably never solve, right? No, it's still got that. Okay. Anyway, there it is. So you can look at the velocity plot. You can see how it's smooshed out. Andre showed this before. If you click on the top plot item here, where it says zone displacement magnitude, change that to label. Change the label to state. See, all this stuff is shearing. It's failing in shear now. This is the shear end, means it's shearing now. Two of these guys sheared in the past, and all these guys out here, nothing happened to them. So. See how that's the right solution. So how much detail we want to get into here, but one of the reasons this is in the manual is to test different types of zones. So probably everything we've done up until now has been using four-sided zones. These are the most accurate. Often, if you have really ugly geometries, you can't fill them up with four-sided zones. It's not always possible to do that. So you might end up with, well, you could fill anything with triangles. So it's like a mathematical theorem. You can fill basically any shape with triangles. So you can always mesh with triangles. So there's another example here. If you click on the one that says NMD try, it's the same thing with triangles. You can run that. You go and look at the velocity plot. You can see how now we're looking at triangles instead of quads. Back to what was it? Point showing before displacement. So if you run that triangle one, you'll see you get pretty good, still pretty good match to the solution. Now there's a trick here. Go back to that data file. There's this wacky command that you've never seen before, I assume. The zone nodal mixed discretization on. What that is essentially turning on some fancy calculation that makes the triangles behave more accurately. And I certainly don't want to get into the math behind it. It's somehow averaging the stresses at the points where the triangles come together to make it more accurate. So I'm just going to tell you, if you have a mesh with triangles in it, that could potentially happen when you have complicated geometries. When you do the automatic meshing in Sketch, you end up with a bunch of triangles in there. You just probably want to use this command. I actually talked about turning it on by default, because almost always you want to do that to get the more accurate answer. There are some very rare circumstances where it causes the model to blow up, so it's not on by default. But most of the time, you probably want to use that if you have time. Well, just for fun, you can turn it off and see what happens. Okay, well, then you can ignore everything I just said. And don't worry about it. If you have triangles, you're in good shape. So actually, even if I turn it off, it's not going to work because it's on by default. So I have to say off. I have to manually tell it to turn itself off. Let's see, crap. Okay. Yeah, there we go. So, okay. It's amazing. It actually doesn't, it gets better, but it doesn't get close to this curve. You can, even if you make these really tiny, it still doesn't get close to this. It's a wacky mathematical problem with triangle zones. Anyway, forget everything I just said. You have triangle zones, you're okay. You don't need to worry about it. Yeah. Okay. Let's open another project then. We'll just run through a couple more little examples, and I'm probably gonna have to wrap this up so we can talk about accuracy. Okay, so now let's open go up one level. Basic F2D models. Discard this one. So if you open that basic F2D models, see this super simple example where it just makes a 20 by 20 mesh, fixes the X direction on the sides, the Y direction on the bottom, sets it to be elastic. So this is just demonstrating using constitutive models. Set zone C model assign elastic. You only need, if you don't have gravity, you actually only need two properties. If there's no gravity, you don't even need the density. You just need Young's modulus and Poisson's ratio. Because we're engineers, most of the time you have gravity, so you want to give the density. So let's say with an elastic model, you need three properties: density, Young's modulus, Poisson's ratio. You solve it. You can just make a plot. Either this displacement, everything makes sense. And you could probably work out the back of an envelope what the displacement is based on the modulus and Poisson's ratio. See that you get the right answer. Okay, X1b, this is exactly the same thing, except that in this case, it's assigning the properties with fish. And so the only purpose for showing you this is that you can assign the properties with commands, or you can assign the properties with fish. We haven't done fish yet, but you see that it's relatively simple. You define a function, you loop through all the zones, you set the Young's modulus property to this, Poisson's ratio property to this, call the function, you solve, and in theory you should get exactly the same thing. There's no difference here. The only reason for showing you this is that just to make you aware that you can assign these things with fish. Again, you could do crazy stuff. You could have it changing with depth or random or whatever. Right? Of course, you can also do this stuff in the model pane. So click this little drop down here. You go to model. Go to the model pane. You can click on all these zones. You go up here and say set model properties. Because they're elastic, it only lets you put in density, bulk modulus, shear modulus. But it's actually built in some of this fun stuff here. If you go down, it's a zone property distribution. You can set it up so that there's like a Gaussian distribution of properties or a uniform distribution of properties, and then you just fill in the standard deviation here. You can even set up a gradient so that the properties change with depth, this kind of stuff. So you can do all that graphically. Okay. The purpose of this example. Okay. Oh, example 2, what it's doing is taking the model we already ran, changing it to more Coulomb material. This is just to emphasize what I said before. I changed it to more Coulomb material, and I think in my head, oh well, I'll just use the same Young's modulus and Poisson's ratio. All I need to do is set the friction and cohesion. That actually doesn't work. Even though you're using the same Young's modulus and Poisson's ratio, you need to specify it again because you switched the material model. So that's what's happening here. 2B is just an example of strain softening. I don't necessarily want to go into the details, but this just shows you the syntax of how you can actually do it. So you give your Young's modulus, your Poisson's ratio, your friction. Instead of giving a cohesion, you say, I'm giving a table of cohesion values. What this table is plastic strain versus cohesion. Okay, so at 0 plastic strain, cohesion is 200. At 0.001 plastic strain, the cohesion is 100. At 0.002 plastic strain, the cohesion is 50, so on, right? So I don't have it in here, but no, this is cohesion. This is plastic strain. I'm essentially saying, as soon as it starts to fail, the cohesion is 200. That's probably what we set for our regular old Moore-Coulomb model. But I want that cohesion to reduce No, and then it's going to go flat. So you get this softening behavior, right? Most of the time in real life, when people are using this softening model, they just give 2 points, 3 points. First point at 0, point down here where it's reached its residual value, and then another point out here to tell it to stay at that residual value. So I would say, 90% of the time when people are using strain softening, they give a table with 3 points in it. 0 at some plastic strain where it hits the residual, and then some other value. Because nobody really has the data to know what that curve looks like as itself. That never happens in reality. But yeah, you just say, I'm using this table to specify the cohesion, and you give the table. And you could do the same thing for friction. You could actually have a changing friction after failure as well. Okay, last example. Example 3 is restoring that elastic model and then assigning null to a few zones in the middle here. Solving it. So if you run X3, have a look at the zones, you can see how we nulled out a few zones here and we get a squishing into the middle. This is about the simplest possible tunnel model we could come up with. And again, the reason for using the null is that you might want to fill it back in. So if I look at X4, I can restore that model and then assign different properties to those guys that were previously null. Assume that it's some sort of backfill. Solve it again. Okay, I better wrap up the constitutive models here. There's a whole pile of slides about these different models. Strain hardening, we sort of talked about already. Cam clay. I mean, if you're a soils person, you probably are familiar with this already. It essentially allows you to have normal consolidation and over consolidation. So you have different, you set parameters so you can have a soil that behaves normally consolidated under certain circumstances and over consolidated under certain circumstances. So that's very, very popular model in the soils world. We have this ubiquitous joint model, which allows you to simulate something as if it had a whole bunch of parallel joints in it. So you're not actually putting in the interfaces, like Andre was talking about the interfaces before. You could, in theory, put in a whole bunch of actual real joints. Most of the time, you don't want to do that. So you could make a material that behaves as if there was a whole bunch of parallel joints in it that are close together. And so you essentially give a joint orientation and a joint friction and a joint cohesion. There's not really joints in there. It's just some fancy math that makes it behave as if there were joints in it. So this is useful for rock models, even potentially maybe soil models if they're like some sort of bedded. Hook-Brown, again, if you're a rock person, you probably know this already. It's basically more Coulomb replaced with a parabola on its side. So get the idea. So more Coulomb is just a straight line. Hook-Brown is a curve, because what happens in real life is when you get to high confining stresses, the more Coulomb material is too strong, right? You're up here somewhere. More Coulomb says, oh, I'm this strong, got a constant friction angle. But in reality, you're only this strong. And so the Hook-Brown accounts for that. It's essentially a curve instead of a straight line. This gives you better results at high confinement. There's a bunch of detail here about Hook-Brown, which I'm not going to go into. Then, yeah, last couple slides. But when you have water in here, it's always using the effective stress to work out if you hit that failure envelope, right? That's basically all you need to know about this. And then you may or may not have talked about this already, but this is a very common and useful thing to do, is if you have some constitutive model that's not elastic, let's say it's more Coulomb. Maybe you excavate a hole or something. You don't want there to be, let's start again. Because this is an explicit program, you make a change to the boundary conditions, you can have sort of a shock wave going through the system, right? Let's imagine you excavate this tunnel all in one shot. You don't do the relaxed thing that Andre was showing you. Let's just pretend you excavate it in one shot. You're going to get a huge change in forces there, right? And because it's an explicit code, you kind of get a dynamic wave moving out from that thing. And this could potentially be enough to cause failure. Reality, you don't care about that dynamic wave causing failure, right? You just want to know the static steady state solution at the end. So if you have a situation like that, you can say model solve elastic. What it does is it turns everything to be elastic, so essentially infinite cohesion and tension strength, solves it, and then turns it back to being its regular cohesion and tension strength, and solves it again. So it's if you say model solve elastic, it actually solves it twice, once elastically and then once elastically. So what that means is that when it makes everything elastic, you can have humongous stresses, changes, and boundary conditions with gravity or whatever you want. And all those waves are going to bounce around in there. It doesn't matter because it's elastic, nothing fails. And it's going to come to equilibrium, work out what the stresses are, change everything to be plastic or potentially plastic. And then things might fail depending on what the stresses are, but not necessarily due to these gigantic force changes, just due to the sort of static stress. I don't know, does that make sense? And you can also say model solve elastic only, because sometimes you might want to say model solve elastic only, save it, and then say model solve. So you can just check after the first step that everything's okay. You know what I mean? So you don't, like I was saying before, you might want to run a case where set everything elastic, make sure everything's okay, and then turn it into more Coulomb. You can basically do that with this one command instead of having to go through by hand and changing all the properties.